Hello. So we are starting a new chapter, chapter 14, which is on partial derivatives. And partial derivatives are a special type of derivative. Okay? So, in order to learn about partial derivatives, we first need to learn about functions of several variables. So, the calculus that we've learned, the first year that you were learning calculus, was only concerned with functions of one variable, right? Functions of a single variable, right? So in other words, you have one input. Usually it was x or t, and you have one output. And that was usually like f of x. So to say if the input was x, then the output was f of x, or etc. But as we know, in the real world, physical quantities and not just physical quantities depend on more than one variable. So that's why we learn about functions of several variables. Okay? And our goal in this chapter overall is to extend the basic ideas of differential calculus. Differential meaning you're taking derivatives. How do you take the derivative of a function that has more than one input? Okay? So the first step, of course, is going to be to learn about functions of several variables. And we're just going to learn how to just learn about the graphs. Now, of course, we know already in Mathematica there is a built-in command, contour plot 3D. And contour plot 3D will allow us to graph any function, right? So any function f of x, y, z equals 0, right? And then we can put in so you put in your function here, f of x, y, z equals 0. And you put in the domain for x, maybe it's the domain for y, and the domain for z, right? When actually that ending shouldn't be a curly, it should be like that. But lots of times you have functions that have more than three variables, um, and it's important to understand how the graphs of functions are related to the inputs. So we're going to study functions from 4 different points of view: verbally, which is a description of words, a table, an explicit formula, and visually, which is with a graph. And the key word here, key phrase, level curves. These are very similar to the traces that we saw in the last chapter. Okay, so let's do an example. What is a real world situation where you have a function that depends on 2 variables? Temperature. So the temperature at a point on the surface of the Earth can depend on longitude and latitude of the point, right? So you can think of T, which is the temperature, being based on 2 variables: the longitude, which is the up and down, and the latitude, which is left and right. And then this would be the way to indicate that our function f, right, T, which is temperature, T is a function of x and y. Okay. Here's another example. This is a geometric example. If we are interested in the volume of a circular cylinder, so that looks like this, right? So the top and the bottom are cylinders. We want to know the volume. We know that the volume is a function of 2 variables: the radius of your cylinder as well as the height of your cylinder, right? So this is another real world example of a function that depends on 2 variables. Okay, so now overall, if you have a function of 2 variables, what you're talking about is a rule that assigns to each ordered pair in your domain a real number, and the unique real number is denoted by, let's put here, f of xy. Okay, so just as with our functions of one variable, our function will have a domain, and the range of our function is going to be the set of values that f takes on. And this should be xy belongs to domain D. So D is the domain. So basically the domain is the set of inputs of all possible inputs, and the range is the set of all possible outputs of your function. Okay. We often write z equals f of xy to make it explicit that z is a function of x and y. And in fact, when we are graphing, we'll have x, y, and then the output is z, similar to back when we just had y equals f of x. We had x as your input, and then the output is the y value. Okay. So we're just generalizing the notation that we use for functions of one variable. Okay. So a function of two variables is just a function whose domain is a subset of R2 and the range is a subset of R. So remember, the range is all possible outputs and the domain is all possible inputs. So if you can input x and y, that means that your domain is going to be a subset of R2, which is the same thing as the xy plane. So R2 is just xy. Okay. So let's practice a little bit. For each of the following functions, evaluate f of 3, 2 and find the domain. So let me choose a different color here. Okay, so the easiest one is this part of evaluate f of 3, 2. So what do? X is going to be 3 and y is going to be 2. So for this first one here, f of 3, 2 is just going to be the square root. Now everywhere we see an x, we're going to put 3. So it'll be 3 plus, then the denominator will be 3 minus 1. And everywhere we see a y, we're going to replace it with 2. Okay, so 3 plus 2 plus 1 divided by 3 minus 2. So it'll be the square root of 6 over 2. Let's do it for b. So for here, f of 3, 2 is going to be 3 times the natural log of 2 squared minus 3. So that'll be 3 times the natural log of 1. But the natural log of 1 is 0, so that'll just be equal to 0. Okay. Now let's look at finding the domain of the functions. Okay. So to find the domain, you can look at the domain of the first one here. Remember, the domain is all possible inputs. So look, we can't divide by 0, so we know that x better not be equal to 1. Okay? And then also we know that you can't take the square root of a negative number, so x plus y plus 1 better be bigger than or equal to 0. So in terms of graphing this, remember, so let's see here. So if we were to graph this, here's x, here's y, and here's z. So let's zoom in. Now, how do I graph x plus y plus 1 greater than or equal to 0? So I need y is greater than or equal to negative x minus 1. Right, so all I did was solve for y. This goes back to our Algebra 2, intermediate algebra days, where here's
it's 17 hours.
Here's x, here's y. So first I graph y equals negative x minus 1. And then I shade the area above it because I want y greater than or equal to negative x minus 1. Now, if here's negative x, y equals negative x, and now I can drop it down by 1 unit. So this is y equals negative x minus 1. So then y is greater than negative x minus 1 would be all of the values above this line. Okay. Now, how do I translate that over here in 3 space? I'm still going to have my same line. So now, how do I plot this line y equals negative x minus 1? So now, if this is x being positive and this is y being positive, I'm going to want, So if I draw this line right here, this would be y equals negative x, right? And then if I drop it down by 1 unit, if I translate it down by 1 unit, then I get something like that. Okay. So now I have y equals negative x minus 1. And again, I want to include all of the points above where y is greater than that. So we're looking at all these points up here. So this is now my domain, right? But remember, we have to take into account the fact that we also have this condition right here, which is that x can't be equal to 1. So I go in and I eliminate. So this is 0, this is 1. So what I'm going to do is, let's see here. X equals 1 is this line. Actually, this plane is x equals 1, right? Because here's x equals 0 is the same as the y-axis. So x equals 1 is here. So what I want points that are in this blue region that don't have x equal to 1. And so if I were to sketch it, say, with purple, then I would have to go and I'd have to leave a little space around that x equals 1 plane, if that makes sense. Okay. And let's look at this second one here. For the second one, we've got f of xy equals x times natural log of y squared minus x. So the requirement that I have is I need for y squared minus x to be greater than 0, because you cannot take the natural log of 0 and you can't take the natural log of a negative number. So to say that y squared minus x is greater than 0 is the same as saying y squared is bigger than x. And so now, if we just go and sketch this, it's very similar. So remember when if we were just drawing in 2D space, if I wanted to draw y squared equals x, it'd be a parabola facing to the side, right? If this is x and this is y. So in 3D space, we have that same sketch rotated. So it'd be like that. Okay. And now if I want x to be less than y squared, let's see here. How am I going to pick? I want x to be less than y squared. So in order to test this out, I'm just going to pick a point. What about the point 1, 0? So if x is 1, y is 0, that doesn't work. So then the region I want is outside of this parabola. Does that make sense? So if I want x to be less than y squared, then I need to choose the points that are back here. Okay, so that would be my domain, the set of points x, y, such that y squared is bigger than x. Okay, and so here we have just a confirmation of what we just did. And this is showing the line that we had from before, x plus y plus 1 equals 0. You draw that line and then you want to shade the region above it, right? Because you want this inequality here. And you also need to satisfy the x is not equal to 1, right? So the line x equals 1 must be excluded from the domain as well. Okay, and then we do the same thing with 1b and draw that little parabola, right? Sideways parabola, and shade the region to the left. Okay, so the two examples that we had here, So this A and B were very were cases of functions of two variables where we actually had a specific formula, right? So we had a formula, and we could actually plug in numbers and work with the algebraic formula. However, not all functions are given by explicit formulas. So let's go through some examples of functions that are described verbally and by numerical estimates, which means you have a chart, a table. Okay, so here's an example. In regions with severe winter weather, the wind chill index is often used to describe the apparent severity of the cold. Okay, so our formula is going to be the wind chill index. Okay, so our W is the index, wind chill index, and W is based on the temperature and the speed of the wind. So we would write that W is a function of T, which is temperature, and wind speed, V, for velocity. Okay. And now we've got a table that's been just a table of records that was compiled by some U.S. and Canada meteorological service. And here we go. So if you look here, so along here we've got the actual temperature, that's the same as T. And then up top, we've got the wind speed. That's our velocity, V. And so there's a chart. We have a chart that indicates the wind chill index. What is it called? The wind chill index. Based on the actual temperature and the wind speed. Okay. So for example, what is the wind chill index if your temperature is negative 20 degrees Celsius and your wind speed is 5 degrees Celsius? Well, with the wind chill, it feels like negative 24 degrees Celsius, right? You just look up negative 20 and then down here 5, and you see where those numbers intersect. Okay. And similarly, if we were to see if the temperature is negative 5 degrees Celsius and the wind speed is 50, then what is the index? Well, so we would just go over to negative 5. And let's see here, and then 50. And there we are, negative 15. So the bottom line is that this wind chill index is a function of two variables. But we don't have a formula. All we have is a chart of just a kind of a list of numerical data. Okay. So that's one example. Another example is one that's used in economics a lot, and it is the Cobb-Douglas index. Okay, so Charles Cobb and Paul Douglas in 1928 published a study where they came up with a model to describe the growth of the American economy over 20-something years, which includes the Depression. Okay, so for their analysis, they just looked at a simplified view. And the production output, so this is their function, is based on the amount of labor involved and the amount of capital invested. Okay, so even though there's more to output than production than labor and capital investment, this model just takes into account those two. Okay, so the L here stands for the amount of labor, and the K stands for the amount of investment capital. So P stands for the production output. And the key is that, so B is a constant and alpha is a constant. Okay, so they assumed that the relationship between labor and investment capital, right, and the relationship between labor, investment capital, and production output had this general form: B times L to the alpha times K to the 1 minus alpha, right? So in order to figure out B and to figure out alpha, They used, so P is the total production. We already did that. K is the amount of capital investment. We did that. L is the amount of labor. Okay, total number of person hours worked in a year. All that stuff. So what they did was looked at data that was available from 1899 to 1922. And then based off of this data, which was published by the government, they used linear algebra, actually. And they did this is linear algebra, and it's also something that's talked about in statistics. Least squares fit. So they looked at they basically took this data and fit it against that original assumption, which is that the format of the function is going to be like that, right? And so then they were able to fit and see, well, what's the value of alpha and the value of beta that makes the data best fit the equation, okay? And the answer was, it turned out that B needed to be equal to 1.01 and alpha needs to be equal to 0.75. Okay? All right, let's use the model given by the function in equation 2 to compute the production in the years 1910 and 1920. So for 1910, so we would look here, and in 1910, we know that L is 147, K is 208. So let's see how close our function comes to approximating the actual value, which is 159. So we need P of 147, 208. Okay, so P of 147, 208. That's going to be 1.01 times 147 to 0.75 times 208 to 0.25. And using my calculator, let's see, I get 1.01 times 147 to 0.75, and then times 208 to 0.25. Oh boy. 47 to 0.75 times 208 to 0.25. So I got 161.929. Now the actual value was 159. So 161, which is approximately 162, it's not that bad. Okay, in terms of an approximation. And then we can do the same thing for the year 1920, where we can look at these values here, 194 for L, and plug in 407 for K. And the number we'll get will be 235.8, which is very close to the actual value of 231. Okay? So like, imagine how powerful this is, because if you're able to make estimates this good, then you have a lot of financial benefits to that, right? So if you can estimate what's going to happen with the economy, then that lets you know, do you need to increase jobs? Do you need to increase investment in capital, right? You can do a lot with that. Okay, so the production function has subsequently been used in many settings, ranging from individual firms to global economic questions, and it is known as the Cobb-Douglas production function. Okay. The domain, obviously L and K need to be
1715.
Thank you. Need to be non-negative because they represent amount of money for K, and for L it's the number of man hours, and you can't have negative man hours. You can't have negative dollars in this sense. You can't, right? So let's just practice finding the domain and range. Now here, for the domain, again, we just need the denominator, or not the denominator, but 9 minus x squared minus y squared. We need that to be greater than or equal to 0, because you can't take a square root. 9 minus x squared minus y squared needs to be greater than or equal to 0, right? So that's the same thing as saying x squared plus y squared needs to be less than or equal to 9. And if we were sketching that, that means that we can expect, so this is a circle of radius 3. we can expect the graph to be within, to have this domain, okay? So that's the domain. And now how about the range? Well, if we look closely, first, if you take the square root of a number, the square root is never going to be negative, so it's always greater than or equal to 0. But on the other hand, this is going to be less than or equal to the square root of 9, right? So our range is going to be in between 0 and 3. Okay? So in terms of the picture, this tells us that whatever we draw for the range, the graph isn't going to be above 3 units. Does that make sense? So whatever the graph is, it fits in that little shape there, right? Because the range has to be in between 0 and 3. Okay. And the next thing we'll talk about is graphs.